In section 3, we're going to take a look at independence and mutually exclusive. So we have to talk about something called a sample space. And when we talk about a sample space, what we're doing is it's the list of all possible values for an experiment. And we're talking about anything that, and when we talk about experiment, we're talking about anything related to probability. And then the way we denote a sample space is we always do a capital S equals, and then we list our outcomes inside a set of curvy brackets. So for example, if we roll a 6-sided die, we want to know what the sample space is. So we do S equals, and then we list, separated by commas, all of the outcomes when you roll a 6-sided die, which are the numbers 1 through 6. So 1, 2, 3, 4, 5, 6. And then we close our brackets. In our second example, we're given a spinner with very specific outcomes and we want to list the sample space. So in that case, we do S equals, and we do our bracket. Now, it would take up a lot of room for me to spell out all of these words, so I'm just going to use the first letter of each color. Now, if you have repeated things in a sample space, you do have to list them multiple times. So I only have 1 yellow, so I'll do 1 Y. There are 3 blue, so I'll do 3 Bs. There's also 3 greens, so I'll do 3 Gs. And then there are 5 reds, so I'll do 5 Rs. So sample space has to list all of the possible outcomes, even if something is repeated. So just because I only have the colors red, yellow, blue, and green, I don't just list them each once because there are multiples of some of the colors. So we did briefly talk about probability already, but probability is the measure of how often an event will occur. So we talked about probability from two-way tables, but this is a little bit different because we're going to just be given either an event or an experiment, and we need to find the probability from it, not from a table. So probability is always a value between 0 and 1, and then the way you find probability is you take your number of outcomes and you divide it by the sample space. So if we go back to our rolling a die example, I want to know the probability of rolling a 4 on a 6-sided die. So the way we write it is we do a capital P, and then in parentheses you put your outcome. So in this case that's rolling a 4. So the probability I roll a 4, and then equals. So we talked about our sample space above. We know our denominator is 6. So how many 4s are there on a 6-sided die? And there's only 1. So my probability is 1/6. For our second example, going back to the spinner, we want to know the probability of the spinner landing on red, and then we'll also talk about green. So the probability of red, all right, so total number of spaces, there are 12, and my numerator would be the number of red spaces, which there are 5. And then for the probability of green, still 12 spaces, but there are only 3 green spaces. Now in this case, 3 over 12 does simplify, so I'm going to write it as 1/4. In both of these cases, you could also write decimals. 1/6 is not a nice decimal, so I don't want to write a decimal if I can avoid it, especially for fractions like this. Try to leave them either in most simplified form, or if they have a nice decimal that's exact, you can do the exact decimal. So now we've talked about that a little bit, now we can talk about independent probability. So 2 events are independent if the probability of the next event is not affected by the previous event. So independence comes from doing multiple things. So if you're going to pull things out of a bag, draw cards from a deck, roll a deck, roll die multiple times or multiple dice, spin a spinner multiple times. So it's more than one thing. But previously we've just been talking about single events, but now we're going to talk about multiple. So you want to know if the events rolling a 6 and rolling a 2 on a 6-sided die are independent and why or why not. So you have to ask yourself, if I roll a 6 and then I roll a 2, does the probability that I roll a 2 change based on the first event? And in this case, it doesn't. So these events are independent. And they would be because the probability does not change. In our second example, we have a bag of 20 marbles. There are 4 blue, 9 orange, 1 red, and 6 green. We want to draw 2 marbles out of the bag, and we want to know if the events of drawing an orange and a red marble are independent, why or why not. So a key thing you want to look at, especially in instances like this, is whether or not you are drawing with or without replacement. And it will always explicitly state whether or not you're returning something, so if you're replacing it. So in this case, I'm just drawing 2 marbles out of the bag. So I'm going to pick a marble, I'm not going to put it back, and then I'm going to draw a second marble. So in this case, the events are dependent. Okay. And that's because you are not replacing the marble. The total amount of marbles is going to change for the second draw based off of the first. If I were replacing the marble, different situation, because then my total still remains 20 marbles in the bag. So when it comes to finding probabilities based on independence or not, we typically label our events with capital letters. So we'll let the capital letter A denote the first event and the capital letter B denote our second event. So then P parentheses of A is the probability of A, and then P parentheses B would be the probability of event B. So if 2 events are independent, the probability of A and B, so the probability of both events occurring, is the product of the probabilities. So probability of A times the probability of B. Okay. So going back to the examples we just talked about, we're going to let A equal rolling a 6, B equal rolling a 2. I want to find the probability of A and B. So we already talked about the fact that these events are independent, which means I can just go ahead and multiply their probabilities. So the probability I roll a 6 is 1/6. Probability you roll a 2, also 1/6. So when I multiply straight across, and we get 1/36. So there's a 1 in 36 chance that you roll a 6 and then roll a 2. It's the same probability for rolling any 2 numbers on a die, because dice, for our purposes, are always going to be independent. So rolling a 2 and a 2, a 1 and a 4, any combination of 2 die are always going to result in the same probability of 1/36. Okay. For our next example, so going back to our bag of marbles, suppose we replace the marble after we draw. A is going to be drawing an orange marble, B is drawing a red marble. We want to find the probability of A and B. So probability of A and B. So my probability of drawing an orange marble, there are 9/20, times my red marbles, which there are 1, so 1/20. So that becomes 9/400, which 1/36, we kind of have an idea of what that means, but 9/400, not as obvious. So as a decimal, that's 0.0225. So a little over 2% chance that you draw an orange marble and then a red marble. Now we're going to talk about mutually exclusive. So this again has to do with multiple events. So two events are mutually exclusive if the probability of both events occurring is 0. So what that basically means is two events can't happen at the same time. So you're asking yourself, if I do a single thing, can those two things happen at once? So it's not like independence where you have two events. In this case, you're saying if I do things once, can both events occur? So it's slightly different than independence. So for our next example, we know, are the events rolling a 6 and an even number on a 6-sided die mutually exclusive? So you think to yourself, is a 6 an even number? And the answer is yes. So these are not mutually exclusive. Now, if that were a 5 and an even number, they are mutually exclusive because 5 is not even. Or if I had 6 and an odd number, 6 is not odd, so those are mutually exclusive. So going back to our spinner, are the events landing on yellow and green mutually exclusive? So when it comes to a spinner situation, it's can I land on a space that is yellow and green at the same time? And the answer is no. So in this case, these events are mutually exclusive. The way our spinner is set up, actually, every event is going to be mutually exclusive because it's a color. I land on one color. Even if it were between two colors, we're not technically landing on either one, so it's still mutually exclusive. Now, if my spinner had been numbers, then it would be different, because if I were talking about, similar to the dice, landing on a specific number and whether it's even or odd, not mutually exclusive. But if I were to try to say, can I land on a 6 and a 2, those would be mutually exclusive. So when it comes to the formula for that, we let event A be probability of A, event B is probability of B. So if I'm finding the probability of one or another event occurring, so the probability of A or B, that's when mutually exclusive comes into play. We do the probability of A plus the probability of B minus the probability of A and B. So if you want to know the probability of one or another event occurring, you have to take into account the probability that both events occur, because you don't want to count something twice, because you can end up with over 100% probability. So you only want to count it once. So find the probability of rolling a 6 or an even number on a die. So the probability of A or B, so we'll let 6 be event A and our even number be event B. So the probability you roll a 6 is 1 out of 6, plus probability I roll an even number, so there are 3 out of them, so 3 over 6. And then I have to subtract the probability I roll a 6 and an even number, which there's only 1, so 1 out of 6, which gives us 3 out of 6, which is 1/2. So there's 50% chance I roll a 6 or an even number, which is different than rolling a 6 and an even number. Okay. So for our spinner, we want to find the probability of spinning yellow or green. So let yellow be A and green be B. So the probability of A or B. So the probability I land on yellow, 1 out of 12, plus the probability you land on green, 3 out of 12. And because they are mutually exclusive, the probability of A and B is 0, so I don't have to subtract 0. So I just add them together, which becomes 4/12, which is 1/3. So in these last two examples, we're going to first determine if our events are independent or dependent, and then find the probability. So in this case, I will talk about how to find probability of dependent events. So we have a bag of 20 marbles. 8 are red, 3 are yellow, 9 are blue. You draw 2 marbles and replace the first one before drawing the second. Are the events drawing a red marble and then a blue marble independent? If so, find the probability. So in this case, the key thing here is that we have replaced the first marble. So these are independent events because we have replaced. So I'm going to let the probability of drawing a red be A and then a blue marble be B. So the probability of A and B. So red marbles, there are 8, so 8 out of 20 times our blue marbles, 9 over 20, gives us 72 over 400, which does simplify because those are both even numbers. It becomes 9 over 50, which is 0.18. So about an 18% chance you draw a red marble and then a blue marble. If you're trying to determine between if I am multiplying or adding, it's whether or not you see the word and or in the problem. So and always represents multiplying, or always represents adding. So kind of a key thing to look at in the wording of a problem. Okay. So now changing the problem slightly, suppose you draw 2 yellow marbles instead without replacing the marbles. Are the events still independent? Why or why not? So in this case, if you notice, we are not replacing. So these events are now dependent because we are not replacing the marble. So when it comes to finding the probability, because I'm drawing 2 of the same colors, I'm basically doing the probability of A and then A again. So when it comes to dependent probability, the first probability is always whatever the first event is. So the probability the first marble is yellow is however many yellow marbles there are over your total, which is in this case 3 out of 20. My second probability now is changed based on the first probability. So the denominator is always going to change because there is now 1 less marble than what we started with. So in this case, I had 20, I pulled 1 out, I now have 19. The numerator only changes if we're talking about drawing the same thing twice in a row, and like in this example. So instead of there being 3 yellow marbles, assuming the first marble was yellow, there's now only 2 yellow marbles remaining, which when multiplied gives us 6 over 380, which does simplify to 3 over 190, which is not a nice decimal, but it is approximately 0.016. If I were talking about not replacing on the previous example, it would be 8 over 20 times 9 over 19, because I'm talking about drawing 2 different colored marbles. So my numerator didn't change because there were 2 different colors, but my denominator did because I still wasn't replacing the marble. So now let's determine if the events are mutually exclusive, and then we'll find the probability. So in a deck of cards, we want to know if the events drawing a spade or a king are mutually exclusive, and then find the probability. So a couple things about a deck of cards. In a deck of cards, there are 52 cards. Their jokers do not count. There are also 4 suits. So we have hearts, diamonds, spades, which I'm not very good at drawing, and then there is a club. And then there are 13 cards in each suit. You have the numbers 2 through 10, and then you have ace, king, queen, and jack. Okay. So when it comes to our probabilities, we'll let spade be A and king be B. So you're asking yourself, can I draw a king that is a spade? And the answer is yes. So these are not mutually exclusive. So when I find my probability, the probability of A or B, I do the probability, I draw a spade, so that's one of the suits, so they're 13 out of 52, plus my probability I draw a king, so each suit has a king, so that means 4 out of 52, and then I need to subtract my king that is a spade, so there's only one of those, so 1 out of 52. So 13 plus 14 is 17, minus 1 gives us 16 out of 52, which is 4/13, which as a decimal is about 0.308. So notice on every problem I've done so far, even if I had a fraction that could be simplified, I didn't. Because I'm adding fractions, you can only add fractions with common denominators. I did not do any simplifying until the end. It does not make sense to simplify a fraction if you're adding or subtracting. On the and problems, I could simplify a fraction before multiplying because you're multiplying, it doesn't matter if you have common denominators or not. But anytime I'm doing an or probability, always leave it so you have common denominators to start off with. All right, now let's talk about the events drawing an even or an odd numbered card. So even is going to be A, odd is going to be B. So you're asking yourself, can I draw a card that is both even and odd? And the answer is no. So these events are mutually exclusive. So probability of A or B. So even cards, 2, 4, 6, 8, and 10. So that's 5 even cards in each suit, which gives me 20 over 52. Plus my odds, which there are 3, 5, 7, and 9. So there are 4, which is 16 out of 52. And when I add, you get 36 over 52, which simplifies to 9/13, which is about 0.692. So please let me know if you have any questions about sample space, independence, or mutually exclusive, and especially finding probabilities with those.